Okay, in this video I want to show you how to use Ansys APDL, how to generate a script from the Ansys APDL, understand the script more or less, and get the results from the interface in order to run in further analysis. So the first thing that we are going to do is to define the problem that we are going to follow. The problem is this cantilever beam, which we will define in the software using membrane elements. In the membrane elements we will have 2 degrees of freedom. Name that degrees of freedom in x direction and y direction according to the coordinates that we normally follow in Ansys, that we have in Ansys. So we are going to define our beam with a certain length, with a certain height, and with certain thickness, and a load that we will apply. The material load that we are going to consider is the one that we have here, which is ideal plastic material load with certain yielding capacity and a tangent modulus equal to 0. The elasticity modulus is going to be 21,000 kilonewton per square centimeter, as we normally use. Now, one of the first things that we would like to know is which is the load that we are going to apply to the model. So in that sense, I have this diagram here, which give us a first hint regarding which is the plastic bending capacity of the section that we will spec. Now, this capacity only consider bending, but you have to remember that in this case we also have shear. So this is a first approach. Probably when we run the analysis we will see that the results differ a little bit. So the plastic bending capacity is going to be equal to the force that we have here, P, multiplied by the corresponding lever arm, and 2 times, because that goes from the center of gravity up and down. So 2 times Z times P. So Z is equal to the height of the beam, half, and to the distance to the center of application of the load, that is 1/2 of this half of the beam, so 1/4 of the beam. The load is going to be equal to the corresponding area that we have in the section, in this half of the section, multiplied by the yielding capacity, so H half times B times Fy, and everything is multiplied by 2 because we have this force in the upper and lower side. On the other side, we know that the reaction of the bending moment here, My, is going to be equal to P times L. So we know first that the load that we will apply has certain magnitude that follow this equation that we have here. So we are going to put this data as an input in Ansys, and we will see how things works. I'm going to move this to the side. So for running Ansys APDL, if you have Ansys installed, you can just click on the key Windows and then write down APDL, and you will have here immediately the mechanical APDL. Have to wait a little bit until that runs. So this is the interface of the APDL, very different to the workbench. And here we have 2 windows. So one window is the one in which we are going to run we're going to create the model, and a second window, this is the black one here, which gives us more information regarding the model that we are doing, and when we run the analysis especially. Now I always like to start by creating a folder. In this case, this folder, I have it in my desktop, example APDL, and in this folder I'm going to save all the information from this model. So normally I go stepwise. I go to files, change job name. I define certain name for this model. Let me just call it example 1. Example 1. Okay. Then file, we change the directory. I'm going to select the one that I have here, the example APDL, and then file. We can change the title of the model. Again, the same, example 01 title, for example. And then we can just put here save as job name dot database in order to have already something saved here. I also would like to immediately write this dv log file, which is the file that is going to give us a hint about which are the commands that represent every step that we do in the model. So I just call it example1 as well, maybe command. Okay, and then you see this file here. We can open this file with a text editor. I normally use this one, which is called Notepad++. It's very good because you get updates in real time. And here you can see all the commands that we have run up to this moment in the model. So we have defined here the name of the file, we have defined the directory, and we have defined a title for the file. Then we have just saved the database. You see that here there is an exclamation mark. The exclamation mark is a comment in Ansys APDL. So if you would, for example, run this model, this script on a second time, this wouldn't be saved because this is commented out. If you want to have that saved, you need to comment that out, comment that, uncomment. And here you have the save of the log file, which is the one that I just did. So this is something that we are going to use very often. I'm going to copy this to save this file, let's say stepwise, while we are developing the model. So for example, in these windows of Ansys, here we have the steps that we can follow for doing the model, and here we have this command prompt. In this command prompt we can put the command that we want to run. So for example, if I do a comment and I put save in file, click enter, nothing happens here. But if I paste this line here without the exclamation mark, and I copy and I paste that here, and I click enter, I click on the file here, you see that the file is updated, and with the comment I put, and also the saving. So we can go stepwise, saving, creating comments and saving the file in order to see how the steps of the modeling process works in terms of a script. So for example, the first thing we are going to do is to define the element type. So we go here to the preprocessor, we select the element type, and we add an element. Here there is nothing. We can add here a solid with 4 nodes, which is a membrane element. We click and OK, and then the element is added. I can close, and then I can just paste again the command for saving the file. If I press up, somehow I go back to the previous command that I have used, and then I don't need to paste it. I just press up and down to find the one that is for saving the file. Click enter, and then here you can see that you have the comment, define the element type. This is what is done in the pre-processing part, prep 7, and we have defined an element type equal with the tag 1, which is element plane 1A2, which represents a membrane element. I can edit this element type to define the theory. So we can click here Then we have the element type. We go to options, and here we have different behavior. Plain stress is one option, and plain strains is a second one. Normally we would work with plain strains with certain thickness of the element. So this is the one that I'm going to select now. You can check what means to work with plain stresses and plain strains. Close. I save the file once again. I press down, and here is the saving, and I go here, and here you see the edit element type, how the option works for defining the element. You have to maybe check the documentation about this key up, because we have different definition here. But if you go to Google and you put the key up APDL, you will see a description about what the command is in general. Set the element key option, and then the arguments of the column of the command. So first I type, and here you can read what this argument means. Canum, number of the key option to be defined, value, the value of the key option. Anyway, I mean, at this point that doesn't play that much importance, because in general the definition is going to be something constant, so it doesn't matter that much. But later we will see other things that we can somehow parameterize. Okay, so we have defined the element that we're going to use. Now we're going to define nodes. I'm going to write here a comment, define nodes, and we do that here in the modeling, create key points. The key points are going to help us to define coordinate x, y, and z, that then we can connect with lines, and then we can create areas using those lines. So we click in here in active CS. Here you can put a key point number. I prefer not to do that. I just put the coordinate. So we're going to start with 0, 0, 0. We apply that. That would be the one that you don't see there. Then we're going to define, at this point we're going to define the length of the beam with certain specific value. So for example, in x 50 centimeters, then we have the node 2 at x 50 centimeter. Then we're going to say that the beam is 10 centimeter high, and then the node which should be here at the location x equal to 0, but the height 10. Then I have the 4 nodes. I can save the file again to see how the nodes are defined in this case. So you see that here is the 50 that represent the length and 10 that represent the height. We can connect the node now using lines, creating lines, and we can go here to lines, lines, a straight line, and we can create the line just by connecting the corresponding node. 1, 2, 2, 3, 3, 4, 4, 5. I click in cancel because sometimes when you click in OK, something happened that you don't want to happen. I save, and now we see in the script that this is the command for creating the line, LSTR, with the corresponding key point that you want to connect, key point 1 to 2 that are defined here. These key points, you see that they don't have anything here, but since they are somehow organized, automatically the software recognizes that this is the key point number 1, 2, 3, and 4. Anyway, it would be possible that you put the name, and maybe it would be more organized, but that depends on how you want to do your model. So now we have the key points, and we have the lines. We are going to define an area, arbitrary area, considering lines. So we're going to select the lines that are there. We don't see them now because of the modification of the window that I did, and we're going to click in OK, and then the area is created. I forgot to put the comment here, but I'm going to put here previous commands were for creating area, and now we just save. And I don't have the comment. We have this comment thing which is commented out replot because I moved the windows, so that is also automatically saved here. Afterward, you can just clean your command file in order to run this in a cleaner way. So here you see that there is a command for selecting the lines. The lines are selected here, 1, 2, 3, 4, and then an area is created according to the line that we have selected. These things, maybe it's not that important that you understand them, because you can just do a first model and save this thing automatically, and it's not going in general, if you use always the same cross section or the same geometry, the geometry will be normally modified here. We can put some parameter here, and then this would be remains always the same. Okay, so we have the geometry, we have the area. Now we want to do a meshing or define the mesh that we will use. So I'm going to use this mesh tool, a comment first, doing the mesh, this mesh tool, and here you have different alternative for meshing. So we are going to match the lines here, the line that we have defined at the beginning, set line 1 and 3. You see here that we have selected 2 lines from a maximum of 4. Clicking OK, and then we can define here the number of divisions that we want in the line. Let's say that we want to divide that into 20 elements. Yeah, 20. Click in OK, and then the lines, you see that they are somehow divided. We can do the same again for the line 4 and 2. Click in OK again, and then those we want to divide that by 6 times. Okay, then those lines are divided. Now why is the reason I'm doing this is because this division of the line is going to allow me to have a mesh which is mapped. So then we will have perfect rectangles in this case with the number of divisions that we have defined. So when we go now to match the area, we can put here map it. We can select the area that we want to match, click there, click in OK, and then you see that the match is according to the map that we have defined. So 1, 2, 3, 4, 5, 6 elements in this direction, and 20 should be in the other direction. We can close this, and we save again to see how that is defined here. So here you have many lines that define this matching, the match of the lines. Here are the 20 divisions that I have defined, the sec division in the other direction. We can just later put those as variables that will define the model. Okay, so we have the match, and now we can apply the load in this case. I didn't calculate which is the value of the load. Let me just do that very quickly with Excel. And the equation that I define here. I forgot one important thing in the modeling. We will do that in the next step. So we have defined length equal to 50 centimeters. The program works without any unit, so you need to be constant by yourself with respect to the units that you want to use. You have to be consistent. The height of the beam, we said it was 10 centimeters. B, we have not defined B, it's something that we are going to use. do. Fy, we have also not defined the material properties. We will do that as well now. Kilonewton per square centimeter. And that's pretty much everything that we need. So the B, we are going to use 2 centimeters. So here the load P that we can apply, that will define somehow this plastic capacity, should be equal to h squared times B times Fy over 4 times L in kilonewton. 23.5. Funny enough, is the same that we have here. So this load is supposed to develop a full bending capacity. However, since we have shear, maybe we are not going to reach this load, or maybe the load would be less. So we are going to see what happens in this case. So I'm going to define the thing that I forgot to define previously. So first we're going to define the thickness of the plate. This is very important. Since we are using this element type, which is a membrane with certain with plane strain and with thickness, the thickness we can define that here in the real constant. In this part of the menu, we can add, and this constant, this thickness, is going to be related with the element that we are selecting here, the element 1, and here we can define the thickness, which is going to be 2 centimeters. Click in OK, close. We save to see how that affects the result. So basically what we do is that we associate these constants R to the element type 1 with a thickness with a value equal to 2. Now we're going to define the material ferroelastic part. That is done here in the material properties, material models, structural, linear, elastic, isotropic. Ex is equal to 21,000, the elasticity, and the Poisson ratio equal to 0.3. Click in OK. I'm going to close and save. So this is the material elastic part. And now we're going to define material inelastic part. Again, material model. It's the same material model number 1, but now we're going to add the nonlinear part. Nonlinear is going to be inelastic. We're going to consider rate independent plasticity with isotropic hardening. Even in this case, we are going to consider that hardening is equal to 0. Misses plasticity, that is the way the yielding is defined, and bilinear case. So the yielding stress is 23.5 and the tangent modulus equal to 0. Click in OK, and then you see here that the material model number 1 is defined according to those 2 parameters. And then we save. And we see here how the inelastic part is defined. Here is the yielding parameter, and here is the hardening, which is equal to 0. So now we're going to define the load. The load we're going to apply here in this border equal to 22.5 as we have calculated, and we can define the load either here or in the solution part. We're going to do it here in the preprocessor again. So we go to loads, define loads, apply a structural, and here you have displacement, force, moment, pressure, different alternatives. First we will start with the force on the node. We're going to apply the force in the node here that we have there. We click in OK, and we applied a force in the direction Y, because Y is vertical in this case, with a value equal to 23.5. Click in OK. I applied the force into the upper direction. We're going to leave it that way, but it would be better to go in the other direction. But anyway, we leave it that way to see how that looks like. We save again. Define load. You see that in this case you select certain node, the node number 22, and we apply the load with the in the direction Fy with the value 23.5. Now we're going to define the boundary conditions or supports, and this is applied in this same place that we are here. So this is defined as a load, but the difference is that this is defined as a displacement. So we can apply this displacement, which is going to be the boundary condition equal to 0 displacement, in a line or in a node. So we're going to use the line in this case. The line is the one that we have here, the line number 4 that we defined previously. And we are going to restrain all degrees of freedom, so X and Y in this case. Click in OK, and you see there the restraint. We save again, and we see how that looks like in this case. Again, here is a command for selecting things. We select the line number 4, and we apply this displacement on line equal to restraint in all directions. So we have at the moment defined everything that we need for running the model. So we can now go to the solution part and just run the model, but that wouldn't give us the information that we want. Before running the model, we would like to define certain parameters that are important. Those parameters are that we are going to run the analysis stepwise, and we are going to consider certain number of steps, and we are going to save the information of every step. So let me just see here. That is defined here in the analysis type, solution controls. We can define here that we have number of sub-steps. So we're going to define 100 sub-steps. The maximum number of sub-steps is going to be 100, and the same for the minimum. So in that case, we somehow define specifically that it's going to be always 100 steps. If you select certain different number from maximum and minimum, then the steps might change. Here we are going to select that we write every sub-step, every n sub-step, because we want to n sub-step, every n number of sub-step. Write every sub-step. That is what we want. And we're going to consider large displacement as well. We click in OK, and we save. I didn't put a comment, but I should put a comment that definition of the solution options, and then I can save. So from this line that set solution solve, we have defined the nonlinear geometrical that we are going to use, the number of sub-steps. We are writing everything. Sorry, not this one. Erase all that we are writing. We write all the results, and that's it. Now we are ready to run the model. So if we go to solve, current load steps, click in OK, the model is going to be solved in ideally 100 steps. So here you see that we have a little bit more of 100 steps because there are some iteration in the steps that are nonlinear. So up to this point we are in a linear curve, but then you see that somehow the convergence has increased, and then there is a iterative procedure in the software for decreasing this error that exists between the applied load and the internal load somehow, and this happened many times in this nonlinear part. We click in close, we close this thing, and now somehow the model has been solved. Post processor, and I don't know, we want to see the results, so we go to plot a contournal plot from the nodal solution, and we want to see the stresses, von Mises stresses. You see here the von Mises stresses from the model. Now the first thing that you should ask yourself is if this good, not good, how it is the behavior. Probably you see that there is a nice somehow distribution of the stresses. You see, okay, it looks nice, I'm happy with that. But you're seeing with another solution, you see the average solution in every node. So it's not a really good representation of how the stresses are, if the stresses are well calculated in every node. Normally I would prefer the element solution, because then you will see which is the actual discontinuity that exists from stresses in your model. So here you see that it doesn't look that nice as the previous case. You see the discontinuities that exist, for example, here in this blue color there. So in the center of the beam, maybe the solution is not so accurate regarding the stress distribution. At this point it looks okay, but I would say maybe a bigger match would be better. Now more importantly, it's here. The maximum stress that is written here is 24.89. Why? Because the model, the program is showing you the solution in the extreme of the element. So let me just see if I can show something here. I can draw something. So you know that in each finite element you have your element. We have to wait a little bit until that appears there. Well, in each finite element you have your extreme nodes, but the analysis is not done in the extreme nodes. It's normally done in the Gaussian points, the green that you have here. So the solution that we obtain are normally associated with these Gaussian points. The software now is showing you the solution at the nodes, but what the software is doing is extrapolating. So here the result is 23.5, and then by extrapolation it reached at this point a value of 24 point something. So it's not actually that much correct what we see there. We want to see the result in the Gaussian point. We can do that if we go back to the solution and we write down the next parameter in the command prompt, defining solution at Gaussian points. The solution extrapolation is set to no, so we will see the solution at the Gaussian point. I click enter, and then we run the model again. We will see how the result change in this point. Close. So now we go again to the post processor and element solution, the von Mises stress. Now you see the maximum value of 23.5, which is the one that we have defined. What we see here is that the section is not fully plasticized. The plasticization somehow is happening at this point a little bit, but we have not reached the full plastic capacity of the section. Why? Because we have this interaction between bending moment and shear force. So in order to find which is the maximum load, we can just increase the load and then see how that works. So I'm going to stop the video here, but I'm going to proceed with the next thing in another video.